This is the first of 3 videos on section 2.3, and I'm going to be introducing the concept of relations and functions to you. So let's just take a look first of all about some ways that we talk about things in our common English language, and it'll set us up for what a relation is in math. A lot of times, one quantity can be described in terms of another quantity. So, for instance, your letter grade in this class depends on a numerical score. Or if you go to the gas station, the amount of gas, the amount that you pay for gas is going to depend on the number of gallons you purchase. And then lastly, the dollars spent by the average American would depend on the expenses of that particular household. So what we have in math is if we've got a value of y and it depends on whatever x is, then we would say that y is the dependent variable while x is the independent variable. A relation is going to be a set of ordered pairs, or you could say coordinates. More specifically, a function is going to be a relation. So a function is a set of ordered pairs in which for each distinct value, there is exactly one value of the second component. Now, I know I just read that to you and it doesn't mean a whole lot, but here's the deal. A function is not allowed to have x repeats. That's the bottom line. A function cannot have x repeats. So if you can just remember that, then it'll be easy. All right, so for example 1, each of these is a relation. It's a set of ordered pairs. Is it a function or not? So when we look at the first example, set M, notice there are no x repeats. So yes, this is a function. For the second set, again, no x repeats, it's a function. However, on the third relation, set P, we do have a pair of x repeats and the y's are different, so this one is not a function. This next statement is another way of saying the exact same thing. In a function, no two ordered pairs can have the same x value with different y values. Again, that's just another way of saying no x repeats. All right, let's talk domain and range. In domain and range, all of your x values are called the domain. And I like to throw out here that not only is this called domain, but visually, these are my left and right values, my left and my right values. My y values are going to be called my range. And these are going to be my down values and my up values, or my bottom values and my top values. Think about y's, they're always ups and downs. So, and I like to start with the bottom values and work my way up. Example number 2 says that we should give the domain and the range. All right, so here's a set, part A, and all of my domain values are going to be my x values. There's only 4 of them, so I can list them out, -4, -1, 1, and 3. Notice that I'm using a new notation with you. In the last section, we talked about graphing notation, interval notation, and set builder notation. All 3 of those notations are usually only used when my set has an infinite number of values. Listing notation is when I only have a few values. So since I only have 4 values here, I can list. And when I list, I use those curly Q brackets. It's not the same as set builder notation. It is just a list of all of my values. My range is going to be a list of the y values, so -2, 0, 2, and 5. And we're going to say that, yes, this is a function. The second part of my instructions here told me to determine if the relation was a function. Yes, it's a function because I don't have any x repeats. All right, so for part B then, what I want to do is I want to take my example and I want to write it in the ordered pairs. It's easier to see it if I have them written in ordered pairs. So I have a 1, 4, a 2, 5, a 2, 6, and a 3, 7. Notice I have a set of x repeats. So first off, this is not a function. In my domain, I'm going to list my X values. One of the things that I want you to notice is that once 2 is in the set, it's in the set. You don't have to tell that it's in the set twice. And so it's just simply in the basket. And so my domain is a 1, a 2, and a 3. My range is going to be a 4, a 5, a 6, and a 7. For part C, again, very similar here. You'll notice that my domain is -3035. My range is just one value. Again, notice I'm not repeating. Once the 5 is in the set, I don't need to say over and over and over again that it's in the set. Is this a function? Yeah, it's a function because I don't have any X repeats. All right, let's go down to finding the domain and range when I have a picture to look at, not just a set of ordered pairs. I'm going to do these 4 questions out of order. I'm going to start with part C. And in order to do this, I've got a rectangle here that I'm going to use. So let me zoom in a little bit there. All right, so what I want to do is I want to fit my rectangle snugly around my figure. So for the left and the right, again, only look at the left and the right. Don't pay any attention at all to the top and the bottom. Only look at the left and the right. Remember that my domain, this is my left and my right values. So you'll notice that for the box on the left and the left and right sides of the box, I'm starting at a -5, I'm ending at a +5, and I'm using the 5. I'm including the 5. So I'm going to use square brackets on those end values. Now let's switch our brain over and talk about the top and the bottom of our rectangle. So once again, when I talk about the top and the bottom, let's make our rectangle fit snugly. I don't really care about the left and the right now. I only care about top and bottom. And you'll notice that the bottom of my box, always work your way from the bottom up to the top. The bottom of my box starts at -3, and then the top of my box goes to +3. And once again, I am using those values. All right, now let me drag my rectangle over here, and let's go to this example, part D. All right. And the first thing that I want you to notice is that in my parabola, which is what I've drawn here, notice that there's arrows at the bottom. These arrows tell you that this parabola goes down and down and down and down and down forever, but that's not the only thing they tell you. It also tells you that the parabola is getting wider and wider and wider and wider as it goes down. So when I only think about the left and the right sides, I'm not going to snug it in like this because my parabola is going to get wider and wider and wider and wider and wider and wider and wider. So my domain for this guy, because it keeps getting wider and wider and wider, my domain is going to be all real numbers from -infinity to +infinity. My range, on the other hand, let's start at the bottom and let's work our way up. Okay, and because those values on bottom or those arrows are on bottom, it's going to go down and down and down and down. But on the top, I do have a stopping point on the top. So when you think about starting at the bottom and working your way to the top, the bottom starts at -infinity and the top will stop at the value of 4. And I'm actually using that value of 4, which is why I used a square bracket on that. Okay, so now without the box, let's go up to part C and let's think if we can do the exact same thing here. Imagine that you have a box. So the left and the right sides of the box would be getting wider and wider and wider. So we would say that our domain is -infinity to +infinity. My range is going to also going to go down, down, down forever and up, up, up forever. So it's also going to be from -infinity to +infinity. Notice that all 3 of these in my domain and range, I used interval notation because there were an infinite number of values in the domain and an infinite number of values in the range. However, when I look at part A, notice that my domain, again, this is x values, I'm only using a -2 x value and a 4 x value. So my domain, I've now switched over to listing notation because there's only 2 of these values. My range, my y values, I'm only using a 3y value and a 0y value. Interestingly, listing notation does not have to be written in order, like interval notation has to be written in order. All right, now let's go down to this next little gray box here. This is another way to look at a graph. This won't tell you about domain and range, but it'll help you to know whether or not your graph is a function or not. Remember, function says no x repeats. Well, another way that you can tell if something is a function when you look at its graph is by using the vertical line test. And the vertical line test just simply says that a vertical line, an imaginary vertical line, intersects the graph in no more than 1 point at a time. So what I've got here is I actually made myself a vertical line. And let's see here. I'm going to take this vertical line across each one of my functions. I'll cross it. And so what I want to know is, does my vertical line touch more than 1 point at a time? Oh, look right here. My vertical line touches 2 points at the same time. So we're going to say this is not a function, but you'll also notice there were x repeats. So that's not a surprise. All right, let's go over to the next example. Well, let's see, as I come through, it's only touching 1 point at a time, 1 point at a time. It's only touching my line 1 point at a time. So we would say that this one, yes, it passes the vertical line test, so therefore it is a function. Let's take our vertical line down here to the parabola. And notice that I'm only touching 1 point on my parabola. My vertical line is only touching 1 point, only 1 point, only 1 point, only 1 point. So yeah, this guy only touches 1 point at a time. I don't have any x repeats, so it's a function. Last but not least, let's take our line over to this oval thing. It's actually called an ellipse. And all of a sudden I see that my ellipse touches 2 points at the same time, so it is not a function. All right, so this is where my first video is going to end, and check back to get the second video.